The title of our talk is Correct Material Selection and Lifetime Prediction of Elastomer Parts using FEA simulations. And this is the agenda for our talk. I will talk about the correct material selection in the first section, and then my colleague Dr. Wehrmann will talk about the FEA simulations of the of elastomer materials. Okay, let us introduce ourselves. My name is Murat Gulkur. I am Material Development Manager for Semiconductor segment based in Trelleborg Sealing Solutions, Tewkesbury in the UK, and I will talk about the material benchmarking test today. Christoph?
Hello everyone, this is Christoph speaking. I'm based in Stuttgart, Germany, working for Trelleborg Sealing Solutions 2, and I'm responsible for simulation methods, developing new methods. And I have a colleague, his name is Amok, who did the main work here. He's an FEA engineer, also working on simulation a lot. And then another colleague, Peter Grass, who's the semiconductor segment manager of Europe. He also put his things to this presentation.
Okay, so I would like to start by introducing our company, Trelleborg Sealing Solutions. So we are a global company, mainly supplier of polymer-based critical sealing solutions for several industries like aerospace, semiconductor, oil and gas, and many others. So as I said, we are a global company. So we have 28 manufacturing sites all over the world. We have 9 R&D centers. We are present in more than 40 countries all over the world with 54 sales offices, marketing companies, and we have many other customer service hubs and logistics centers all around the world. So I would like to start with sealing material selection. So when we talk about the seals, obviously, I mean, seals can come in many shapes and materials, from molded polymers to even like grease can be a sealing material. But today we will talk about elastomer seals. So the important thing with the seals, obviously, the design is quite important, as well as the material itself. So both really, drives the performance of the seal, both design and the material itself. But especially for semiconductor applications, we believe that materials are slightly more important because they can also contribute to the yield quite a lot because of like particulation or plasma resistance type of properties that are not needed for other applications. And it's always a little bit risky for the end users, for OEMs or fabs to qualify a new material because of a new material introduction. It can cause some problems in the chamber. It can cause some waste of time. So as a supplier at this point, our duty is to provide as much data as we can provide to our customers to have the confidence to put our materials in the chambers. So what things to consider when we specify a new sealing material? So obviously the end user, either an OEM or semiconductor fab, I mean, they expect the best performance. Obviously, I mean, everybody expects the best performance. And in ideal case, I mean, it should be just, one material fits all. For all the processes, just one material to remove the complexity. However, it is not always possible. So because there are lots of different parameters in a process, like process type, the location of the seal, the process gases, chemicals, the temperature range, the node size, purity required, and obviously expected lifetime from a seal. By considering all these as sealing material suppliers, sealing part suppliers, we also need to check lots of other parameters like filler type, the design. Is it going to be an O-ring or custom design? What we recommend for the best performance, and also from the material point of view, lots of testing about plasma resistance, chemical compatibility, as well as mechanical testing. So recently, we developed in Trelleborg Sealing Solutions Tewkesbury a new range of perfluoroelastomer or FFKM materials, 4 new materials, and we created this Isolast PureFab material range. And we have done quite a lot of extensive benchmarking against a wide range of competitor materials well known in the market in order to mitigate the risks for material qualifications for our customers. And I'm going to talk about those in a minute. So let's talk about the plasma resistance. So the basics. Obviously, the most basic ingredient of an elastomer formulation is the base polymer. So if you specifically talk about FFKM based polymers, obviously they are fully organic materials. Therefore, their etch rates, their plasma resistance is very low, especially when we talk about ion bombardment type of plasma. And traditionally, fillers are blended in these base polymers to create elastomer formulations, elastomer compounds, which will have improved plasma resistance because of the plasma resistance of fillers. The filler particles will shield the base polymer from plasma exposure up to a point, and the elastomers finally have better plasma resistance. So when we talk about an example here, a non-filled material, which means that there's only the base polymer and the curative, the most basic rubber compound or elastomer material we can get. So if you have such a material, as you can see, if you say that this seal is in the groove, obviously in some applications these seals are exposed to plasma, and from the process side, from the right hand side, if the plasma strikes to the material, obviously over time the non-filled material will be etched away as any other organic material. So the advantages of this non-filled material is obviously because of the number of ingredients in the formulation, just curative and the polymer, the purity is quite high. Therefore, the contamination is low, the particulation or chance of particulation is extremely low. However, the disadvantage of this system is having very high plasma erosion rate, and therefore having short seal life, and being a little bit more expensive than other elastomer choices. So when we talk about the filled material, the similar scenario, if the O-ring is in the groove and the plasma strikes, as I mentioned in the previous slide, the filler particles shield the polymer backbone from the plasma exposure, and therefore the etch rate is lower than the non-filled case. But there's a little bit of difference here, because when the non-filled material is etched away, the etched products are usually very small fluoromolecules, and therefore they can be pumped away and they don't contribute to particulation. That's why non-filled materials really provide a very pure system. But if when we talk about filled systems, sometimes those filler particles can become free after the plasma exposure, because they are very much plasma resistant and they can't be etched away. And if they become free, they can cause some particulation in the chamber if an inorganic filler is used. If an organic filler is used, similar thing to non-filled example on the left-hand side will also happen. It's not going to leave particles or filler particles released, but all the etched products will be pumped away. So the advantages of filled elastomer materials, obviously the excellent plasma resistance, depending on the filler, obviously. And usually those fillers provide a little bit better high temperature stability, especially dimensional stability. And the concerns for filled material, because of the higher number of ingredients in the formulation, they can have more trace metal content, low purity, or they can just cause particulation in the chamber. So in Trelleborg Sealing Solutions, we developed a new technology. So that technology, by using that technology, actually we can improve the plasma resistance of a non-filled material significantly, and without adding any fillers, and therefore we have all the advantages of non-filled materials, like having high purity and low contamination, and we eliminate all the concerns about high plasma erosion rate and short seal life, which I'm going to show the results in the next slide. So most of the seal suppliers, they show this kind of bar charts, benchmarking tests in different kind of plasma sources and different chemistries. And when I show these kind of slides, I always say that not all plasmas are the same. So I'll just to take two examples. Both are NF-free plasma, which is commonly used, but on the left-hand side, which is direct plasma, which is more iron-rich, and on the right-hand side, NF-free remote plasma, which is radical-rich. And let's see the results a little bit more in detail. So let's focus on this competitor material. The name is not, important, and let's compare it to the turquoise bars on the left-hand side. So in direct NF-free plasma, that material performs better than, actually significantly better than those transparent non-filled materials, our JPF30 material and the competitor material. But when we look at the NF-free remote plasma, which is commonly used for chamber cleaning, that material performs a lot worse than those translucent transparent materials. Again, turquoise bars, you can say. So this is only one example. If we take like other chemistry examples into account, there are lots of different examples similar to this. That not all plasmas are the same. Materials can behave differently in different plasma chemistries and sources. So another important property that some of the elastomer manufacturers really don't really focus on, which is the stiction. So we believe that stiction is quite important because stiction can cause some problems with the maintenance time. So the service period, actually it can shorten it, and also the time of service can last significantly longer, which means that higher amount of machine downtimes. If it's a dynamic sealing application, then it performs really poor, and obviously because of in some cases leaving some residue on the surface, it can cause higher contamination and particulation due to leaving residue. So we are using this Stiction test method, which I'm going to talk very briefly. So we have either stainless steel, anodized aluminium, or quartz surfaces that we do the test. So we take two of those surfaces and we squeeze the O-ring by 25% between those jigs, and then we put it in the oven 200 degrees for 24 hours. And then after resting for 2 hours, we connect it to our tensile machine and measure the maximum force that we get in order to separate, separate those plates from each other. So, I mean, similar to, I would say, the outcome of these stiction tests to plasma testing, because every material, as you can see, this is some of the data we have. Some materials perform having very low stiction force on one surface. For example, JPF30 on quartz surface, the stiction force is extremely low. So we tried this like 4 or 5 times, and it's always coming out, like this. So this material doesn't have affinity to quartz, while it is quite sticky when we do the test on anodized aluminium. Similar to some for example competitor material, it just all have sticky behavior on every surface. So this also needs to be closely examined when sealing material is specified for an application. So finally, I'll talk about the elastomer high temperature performance. Obviously, the elastomers, they remember their shape. When they are compressed, they go back to their original shape, and it is a quite good parameter that we need to consider to judge the high temperature performance of an elastomer material. And in order to do that, the simplest method is the compression set test, which is a standard test. Actually, while doing this test, we take the material, we compress it by 25 or 18%, and then put it in a temperature in an oven for a certain period of time. And then when we take it out, we measure the recovery rate, and then we calculate the ratio of deformation in percentage after the test. And then we end up graph like this. So on this compression set charts, you can see 3 materials are tested. One of them is our JPF10 material against the 2 different competitor materials, and we did this test for quite extensive time, more than 1100 hours at 200 degrees on the left hand side and 300 degrees on the right hand side, and we found out that the technology we developed, it has significantly better compression set, a lot lower compression set than the competitor materials, even at high temperatures. So I'd like to just summarize what I said. So there are many parameters to consider when specifying sealing materials. Obviously, the benchmarking test, it gives an idea about where how the material is, how the material performs. However, there must be a reference in order to do that. But I mean, we can also do some more comprehensive analysis, and we developed some simulation methods, and they must be applied to predict the lifetime of a seal in real life applications, which my colleague Dr. Wehrmann will talk in the next section. Christoph?
Thanks, Murat. This is Christoph now speaking, and I would like to continue the presentation speaking about the part which considers simulation of lifetime. And what we did is we applied such a viscoelastic network, so such a network you see here on the right, which consists of springs and dashpots. The first part of the network at the top is only one spring, that's the equilibrium spring. So when we wait a very long time, then that's the result. That's the resulting stress response. And in between, we will have dashpots which have different relaxation times. That means they will relax in a certain time, and we have a spectrum. So that means in the beginning, some of these will relax and then others. So we use such a model to do FEAs, finite element analysis, to predict the lifetime of a seal or an elastomer part. You see some formulas at the bottom. The first one is the stress over time, so the stress tensor, that's why it's written bold, and we have an integral because it's a history-dependent material law, so we integrate over time, and you see the shear modulus, the G, is a function of time, and it's multiplied by the strain rate, and then integrated. Strain rate, the small e, is only the deviatoric part of the strain, because elastomers mainly give their mechanic stress response due to the deviatoric strains. The volumetric part is on the right side, the K, the bulk modulus, and then the volumetric strain, the theta. At the bottom, you see how the shear modulus over time decreases. So we have an infinity shear modulus, which is connected to the spring at the top, the equilibrium spring. And then we have GI, which means shear modulus of each network. And we have theta I, which is the relaxation time of each network. And with such a model, we are able to feed CSR data, so compressive stress relaxation in, and then do FEA simulations to predict the lifetime long term. On the next slide, I would like to show one application we applied this method to. It's an automotive application where the seal has a valve function. So you see in red, the area is where the valve opens at a certain opening pressure. And now here it's important that we can guarantee over lifetime, which is approximately 20 years, that we can guarantee over such a long period that the opening pressure is in a certain tolerance. So it should not below a minimum and not above a maximum. In the beginning, it will be close to the maximum, and then it will decrease over time, over years. So we do CSR tests and feed them into our FEA material model, as shown on the slide before. But of course, we cannot do CSR tests of 20 years. So we do them at different temperature levels, and then we use time temperature shifts to simulate or to capture the behavior long term. So we have to do tests at elevated temperatures, and then we can use the shift model to create such a material model which is valid for a long term, for a long time period, so 20 years approximately. And to verify our method, we did some tests on this component. Of course, here again, we cannot test for 20 years, but we tested approximately 1 year, so really a long test here of such a valve seal. And you see, we were able to quite nearly fit or predict the experimental values here. And to make sure it's describing the long time period of 20 years, we did this test at an elevated temperature too. So it's not the application temperature, so it's elevated so that we in the end consider nearly 20 years when we break it down with Arrhenius to room temperature. So, and you see, we can simulate this here quite accurately. So we are sure that we can predict the lifetime, in this case, the opening pressure of our seal or valve in an accurate way. I would like to show another example, a typical gasket we are manufacturing. You see only the cross section here and a little part of that gasket. So it's a heat exchanger gasket, which can have a length of several meters and different 3D shapes, of course. We looked at the cross section here, which is the essential thing or the most influencing part, of course. And we did the simulation here. The colors show the stress. So of course, in the middle, we have the highest stresses because the material is compressed the most here. And from the contact pressure decrease over time, and time again is a long time period, which means years, we can predict at which point it gets down to a critical level where we can have leakage. And that's how we carry out our lifetime predictions. We can do this at different temperatures too. And again, we use different elevated temperatures to have a material data input which can be transferred to a long time period. Here also we did some tests. So you see, again, it's approximately 1 year test. It's not a linear scale, so that's exactly 365 days, I think. And you see here we have some differences, but in the end, at least we have a rough and I think a good estimation of lifetime. In this case, also we looked at the leakage pressure or opening pressure, which the seal can withstand. And yeah, we think that the differences we have here are reasoned by some simplifications. The metal hardware is only modeled rigid, and we don't have the 3D effects. Maybe in some areas of the gasket, we had some different tolerance situations or similar things which influenced the results, so that we had a certain difference here between test and simulation. But in the end, we are satisfied with that. So we have a tool with that, a method at hand, which allows us to give at least a, let's say, rough estimation. In some cases, really quite precise prediction of lifetime. And of course, this is very valuable for us and our customers when we look at the applications. Of course, we have some limitations. We did not look yet at compression sets. The model will provide a certain compression set because some of the relaxation times are very long. And when we look at the compression test standard, Murat just showed how the compression set works. The test works. This will give us some compression set too with our model, but we could improve it by introducing such a plastic element, as you can see on the right here. Then one other thing is shift of relaxation data. It's not possible for large temperature intervals, and because different processes are occurring. And this is also connected to we have aging effects which are not of the same physical mechanism than relaxation. So there also improvements are possible when we look at our model. So these are things we are working on. So that means, yeah, we will soon probably get an improvement of our lifetime prediction method. So yeah, that's also our outlook. Then, of course, we always need to make sure that we also look at other things like chemical compatibility, temperature profiles, and other application relevant topics to make sure the lifetime prediction, yeah, also captures these things which are not all in the FEA So that means in the end, always an application engineer also needs to consider the situation and think of influencing factors so that we can be sure our sealing system will withstand the years requested to it. With that, I'm finished with my part 2. We do thank you for your attention and being interested in our presentation. If you have any questions, feel free to contact us. You see our email addresses here. Yeah, we are happy to answer any question related to this topic. And thanks again for your attention. Bye.